So we are getting ready to venture into some muddy, muddy waters. And because of this, people tend to get a little uncomfortable with the material. And this is where chromatography really sends people into a spiral. But if you pay attention to the videos, if you walk through the calculations with me, if you just kind of make sure you're taking your coffee or your caffeine for the day, then I think that you will be okay from this point on. All right? So let's talk about what this unknown territory or uncharted, I'm not going to call it uncharted, but pretty dingy, pretty foggy environment is going to hold for us. Okay? So what we've discussed up to this point has been handmade columns, and you use your eyeballs to look at the separation that takes place. And you look at colors, and this is where chromatography word comes from, color writing, right? So over time, what we've decided and what we realized is that we don't necessarily need these colors anymore, and we don't necessarily need a handmade column anymore. We can make this method a little more automated, and we can bring in some instrumentation to allow this to make our life a little bit better in a laboratory. And one of the first things that we need to talk about is data that comes from an instrument when we begin to analyze samples on equipment and not on my handmade columns. Okay? So, what you're going to see is basically a graph that would look something similar to this when we start getting data from the instrumentation. And we have a proper term that we use to describe all of the data that comes from a chromatograph or a chromatography instrument in a laboratory. And what we do is that we label this a chromatograph. And that's the proper term that we use to describe the graphical representation of what we see. Okay? So when I'm getting to the point of running my first piece of equipment and I'm injecting my sample and the sample begins to separate and the instrument begins to see all of the components like my eyeballs would if I was doing this in person, then this kind of graph is going to be generated and we call it a chromatograph. Okay? Now each one of these peaks, and that's what we call that, this is a peak. And each peak represents, hopefully, one component. Now, I'm assuming that my job has been done the proper way, and I'm assuming that there's no other methods or no other tinkering that I need to do with the piece of equipment. And I'm assuming that that one peak is one component. Now, that's not necessarily the case. That could actually be a very large peak that has two components that haven't separated out from each other yet. But we're taking it with a grain of salt. We're getting too complicated. We're getting two steps ahead of ourselves. Each component represents each peak. So in this chromatograph, I have four peaks, which means I have four components in my sample that I have analyzed in the laboratory. All right? Now, what does the seeing part? Well, this is a detector for us. And the detector are basically the eyeballs that we use, but it's the eyeballs that the machine uses. And very often, these are UV vis detectors. They can be refractive index detectors. They can be mass spectrometer detectors. You name it. It can be put onto a chromatograph or a chromatography system. Okay? Now, the reason that I say that is because we have talked about all of these pieces in our first instrumentation class called spectroscopy. So everything that we've discussed in the spectroscopy class basically holds true here as well, because these are the pieces that are the detectors for us. Now, if you've not taken that class yet, but you're taking chromatography first, then keep that in mind. Next time that you take our instrumentation classes, you'll be taking spectroscopy. And the reason that we go into the detail that we go into is because these are the detectors that are commonly used on the chromatography instruments themselves. All right, so this is a chromatograph. These are called peaks, and the peaks are picked up by the detector that's on the machine. And there could be many, many others, right? Those are not just the only ones, but there's tons of different versions that are out there. Now, if you've looked on the graph, the chromatograph, we're going to have a starting point, and this is at 0. The axis down here on the bottom is in the unit of time, okay? And most of the time will be in minutes. Now, it doesn't have to be. It could be in seconds or it can be in hours. It doesn't really matter what unit that I use, but it's time relevant, okay? Most commonly, minute is going to be there. On the y-axis, well, depending on what we're doing and what we're using and what detector that we're using, this can change up. So the only thing that I'm going to put here is the signal. So the signal increases and then the signal will decrease back. This, of course, is called the baseline. And when I have nothing going through the instrument at all, this baseline should be pretty flat all the way across. All right? Now, when I inject my sample into the machine, it's going to take time for that sample to basically come out of the column and to be seen by the detector. And then when it gets seen by the detector, it shoots up, meaning a lot of it's coming off at one time, and then it comes back down, which means that that sample is now eventually leaving the column. Okay, the time that that took, and that's always recorded to where this apex is going to be. The time that that took is abbreviated T sub R, and that is called the retention time. Retention basically means to retard, and when you retard something, you hold it back. So we're talking about how long did my stationary phase hold my molecule back, and that is called the retention time. So let's just say that just for the point of this example, this retention time is 2 minutes, and maybe this one is 4 minutes, and maybe this one is 7 minutes, and maybe this one is 8 minutes. Who knows? I've just made up those numbers. But that's how we start to read the chromatograph itself. It's based on retention time, okay? And we abbreviate that T sub R. So each component will have their own retention time. That's very important, okay? All right, well, there's retention times of a couple of different things that we can talk about. One is the retention time of the component. So I'm going to say retention time of the component that is inside of my sample, right? So that's going to be T sub R. Well, there's also T sub M, and this T sub M is typically the retention time of, not my component, but M stands for the mobile phase. Okay, so this mobile phase should not be retained at all. When I put the mobile phase inside of the column, right, so over here is going to be my column, my stationary is filled, my stationary phase is filled on the inside, and I put the mobile phase inside of the column. The mobile phase should just basically go straight through and out the other end, right? It should not be held back. The alumina or the silica or the stationary phase on the inside should not be holding the mobile phase back any at all. However, it takes some time for me to put the mobile phase in the top and for that mobile phase to come out of the bottom, right? It's not just going to fall completely through. It's going to have some time associated with it. And very often, I would see that signal up here in the very beginning of the chromatogram somewhere. And most of the time, not every time, it's going to be a dip. And that dip represents a disturbance, basically. It's a disturbance that the machine has seen, and that disturbance is due to the fact that you've injected just mobile phase into the machine, and that is all, right? So some of these are a dip that goes down. Some of these are kind of a dip or a peak that goes up, but it will be very, very little, very, very tiny. That is not a component. That is the time that it took for your mobile phase to literally run through the column and out the other end. Columns can be short, columns can be long, and that is going to play a factor in how fast the mobile phase can actually go from point A to point B without getting held back. That takes some time and some effort, and that's what TM represents. Okay? Now, if I've got retention time of a component and I've got a retention time of the mobile phase, then I can do a calculation here. And this calculation is T sub R prime. That is what that little dash up here at the very top represents. And that T sub R prime is something that we call adjusted retention time. And basically, it takes the mobile phase into account. So in order to calculate this, I take the retention time of my component that's on the chromatograph, and I subtract the retention time of my mobile phase. And this gives me the absolute time that my column held my component in the stationary phase itself. Okay? So for instance, up here in the example, I said that this component might have a 2-minute retention time. Well, let's say that my mobile phase disturbance happened at a half of a minute. To calculate the adjusted retention time, well, how long did the component actually stay in the column? How long was it actually held up? That's the number that I want to look for. I would take those two and I subtract them. I would do 2 minutes for my component minus a half minute for the mobile phase, if that's what shows up on the chromatogram, and my adjusted retention time would be 1.5 minutes. Right? So it takes into consideration that it takes at least a little bit of time for it to go through the column. And that time added on top of the retaining time is going to be the retention time that you see on the chromatogram. So if I can take the retention time, subtract how long it actually physically takes to go through the column itself, that will give me the adjusted time, which really represents just the retainment of the compound itself. Now, why would we do this? The reason that we would do adjusted retention time is because different labs can use different columns that have different lengths. So if I choose a very short column in the lab, and then another lab chooses a very long column, and we fill it with the same mobile phase and the same stationary phase, my sample should separate the same way, right? The order of separation should be the same. The shapes of the peaks maybe should be similar. The difference is the length of the column. So what could happen is that this would have a different dead time, or what we would call retention time of the mobile phase. This would have its own T sub M. My components will come off quicker because this is a shorter column. And my components would come off longer because this is a longer column. But when I compare these two to each other, and when I calculate an adjusted retention time, then that value should hopefully be the same. So that way, if I'm doing a separation using this setup in my lab, and halfway across the state, someone else is doing the same separation with a longer or a shorter column, if we go through and calculate the adjusted retention times on these components, then our adjusted retention times will match. Our dead times will not match. The retention time of the mobile phase, that will not match. I'm using different length of columns. Our overall retention times will not match because I'm using different length of columns. But our adjusted retention times will be very similar because it takes all of that into account and it really subtracts it out of the equation. Now for us, when we look at these chromatographs, we're not really going to fool with adjusted retention times most of the time. This is just the calculations that's out there that you can use as a corrective factor. However, when we start doing identification and separation in our lab or any lab, you traditionally use the raw chromatograph time that is printed on your report sheet. You can do the calculated, adjust it later if you want. But for the most part, normal times straight from the graph are going to do you well. And that's what we use most often. All right. If you've noticed, the word that I kept using was dead time. That's also some of the lingo that can happen with T sub M. T sub M, instead of mobile phase retention time, can be dead time. Dead time is basically what space, what void is inside of that column that needs to be flushed through with my mobile phase, and how long does that take? So dead time and retention time of my mobile phase are basically referring to the same exact thing. There's no difference in it. Okay? So in the next video, we'll pick up with some more of this terminology and more of these equations. This is your first one out of many. So stay tuned. There's more to come.